Hello, my name is Shing-hon, and I'm really excited to be able to share with you today a piece of work that my SEI colleagues and I have been working on for the past year, on a project called AIDE, or Artificial Intelligence Defense Evaluation. Before I get started, just a quick thank you to our sponsor, which was the Department of Homeland Security, or more specifically, the Cybersecurity and Infrastructure Security Agency, or CISA. We really appreciate their generous funding of this work. Now let's start at the beginning. The genesis of the AIDE project came about because we noticed that a lot of organizations were turning to AI defenses to protect their networks. And we were interested in understanding both why they were doing so and what the ramifications were of them doing so. Now let's start with that why bit first. So there are two major advantages that organizations are hoping to gain by turning to AI defenses. First, to augment their analyst pool, and second, to counter the increasing speed of operation of cyber attacks. Let's start with augmenting the analyst pool. So there's a current shortfall of 500,000 cybersecurity staff positions in the United States alone. And organizations are looking for any way possible to maximize the staff that they do have. And one of the force multipliers they're hoping to leverage is AI. And they're hoping that AIs can do two things for them. First, to address some of the easier alerts, the more routine stuff, and thus free up their human analysts to handle harder problems, the more complex problems that might require really nuanced understanding of the network, the people using the network, and the business purpose of that network. Organizations are also hoping that AIs can catch threats that a human analyst would never be able to catch. That by virtue of an AI being able to ingest gigabytes or terabytes of data all at one time, they can find some really subtle or nuanced patterns that are indicative of some threat that a human analyst would just simply never be able to catch. The second advantage that organizations are hoping to gain is to counter the increasing speed of cyber attacks. So the bottom left here shows an article about the NotPetya attack in 2018. And this attack took out an entire Ukrainian bank's network in 45 seconds. Right? So by the time your system administrator or your operator or your analyst comes back from grabbing coffee or using the bathroom, it's already too late. The damage is already irreversible. To be able to counter an attack that's moving at that speed, you need to be able to move at near machine speeds. And AI is one of the tools that organizations are hoping to turn to gain that capability. So there are some advantages that our organizations are hoping to gain from AIs, but AIs can also go really wrong. So the top article here is about Cylance, which is a piece of endpoint malware detection software. And some researchers found last year that by appending a selected list of strings to a malicious file, which is another way of saying by taking some benign code snippets and appending them to the end of malware, they were able to fool Cylance to the point where they could completely avoid detection of the malware. And in fact, this was a highly successful method. It worked for 100% of the top 10 malware for May of 2019, and close to 90% of a larger sample of 384 pieces of malware. And it's not just researchers that are figuring out how to make our AIs go wrong, it's our adversaries as well. So the bottom article here is about a Russian espionage group called FancyVer, and what they're trying to do is that they're trying to strip down some initial infector piece of software that they have to gain a foothold on a network. They're trying to strip that down specifically to defeat machine learning-based defenses. And that brings me to the purpose of the AIDE project. So our assessment capabilities ultimately dictate how well we can test our own defenses. And it's now public knowledge that our adversaries are working to evade those AI defenses. Our assessors need that same information that our adversaries have in order to be able to accurately gauge our own defenses against our adversaries' capabilities. The nightmare scenario for us is that our assessors come up against one of these AI defenses, and they don't know how to get past. And so they give that organization a clean bill of health. They say, well, your security seems to be airtight. We can't get past. But our adversary would know how to get past that AI defense, and our adversary would be able to get onto our network. And we've now lulled ourselves into a false sense of security. Now, more formally, the problem that we're trying to solve in this project is to understand the capabilities of AI defenses in terms of how well they can detect malicious network activity, and to understand how those defensive capabilities can be bypassed. And the approach we're taking is to develop a testing methodology for AI defenses, both to identify their capabilities and the ways that they can be bypassed. Now, in this initial round of the AIDE project, we worked on a proof of concept testing methodology, but this is something that we're hoping to eventually grow out into a comprehensive testing methodology. Now, what does this methodology look like? It can be broken down into three major categories of steps. So the first category is the setup steps. So we do things like creating a test network environment. We obtain some AI network defenses and put them and install them on that network. In this initial round of the project, we used commercial off-the-shelf defenses because that was what was easily available. We train those defenses on the normal network background traffic that we have when the network is operating normally. And then in yellow, we perform a baseline evaluation. So we have an attack that we execute against that network, and we see whether or not our AI-based network defense actually catches it. And then in blue, we try to bypass detection by that AI network defense. We're using things like obfuscation or data poisoning or both in order to avoid our attack from being detected when we execute it. Now let me talk about each of these steps in a little bit more detail. So let's start with the network. Well, rather, we're going to talk about an organization first, because networks tend not to exist in isolation. They exist because they need to serve some purpose for an organization. So what we did was we created a software development firm. And on the left here, you see the org chart for that firm. And the firm has 99 different employees across 5 different divisions and 3 levels of management. And each of these employees, and thus each user on the network, has their own unique behavior. They have customized work schedules. They come in and out of the office at different times of the day, and they go about their work tasks in a different manner. They have role-specific work tasks. So somebody who on the IT help desk might do things like using remote desktop to connect to somebody else's machine in order to do some IT maintenance task. Somebody who's working in accounting might access sensitive Excel spreadsheets that contain financial information about the organization. We've also assigned each of these users personal hobbies, so that govern their personal use of the corporate network. So if you're into gaming, you'll go to gaming-related websites. If you're into gardening, you'll go to gardening-related websites. In addition to having all of these unique behaviors, we also ensure that each of our users has privileges and accesses that make sense by their role. So you're not going to find some intern in sales having system administrator access to the entire network. That's going to be reserved for the system administrator because he or she actually needs those privileges to be able to do his or her job. Once we defined all these behaviors out, we used an SEI-created piece of software called Ghost in order to actually simulate this user behavior, and we're collecting the resulting traffic for use for training and testing our AIs. If Ghost sounds familiar to you, it's because you may have heard Jeff Mattson already talk about Ghost and how they used it for a different purpose. So what do our AIs actually look like? So the AIs that we evaluated are a combination of static and learned rules. So static rules are likely familiar to anybody who's worked in cybersecurity. An example is, well, if a host sends web traffic to outside of the company, then an alert should be generated. It's incumbent upon the system administrator to ensure whatever static rules exist make sense for the network and serve the organization, and they serve the purpose that they're designed to accomplish. What the AIs have that differs is that they also have learned rules. An example of a very, very simple learned rule is if a host sends out any traffic to a host that is not communicated with in the last 10 days, then an alert should be generated. What's being learned here is what hosts have been, what hosts and a host has communicated with in the last 10 days. This is a very, very simple example of learning. More common in the AIs that we evaluated are complex learned rules. So for example, if a host sends unusual traffic to a host that it has rarely communicated with, and that host is not considered safe, then an alert should be generated. What does it mean for traffic to be unusual? That's a machine learning model. What does it mean for one host to rarely communicate with another? That's a machine learning model. What does it mean for a host to be considered safe? That's yet another machine learning model. And so the AIs that we're looking at tend to combine both static rules with these more complicated learned rules. So we have these AIs. What did we do with them? So we started by training the AIs. And what we provided for training is 1 month worth of normal background network traffic. Now this choice of a month is because this is what the vendors claimed was required to fully train those AIs. After the AIs are done training, we then took a snapshot of each of them. And we used that snapshot for all of our evaluations in this project. Now, it's worth noting that as we're conducting our testing, the same normal background traffic is going to continue in the background because our workers are continuing to work, even if there are malicious cyber attacks going on. Of course, we'll also have the additional traffic that's generated as part of that malicious cyber attack that constitutes the test. Speaking of that test, here's their baseline evaluation attack. So it's a relatively straightforward data exfiltration attack, and it begins with a step 0, or pre-attack reconnaissance. It then transitions into getting initial access on the network through spear phishing. We establish a foothold, and then we install our command and control tools. Those command and control tools are then used to do things like privilege escalation, credential access, or network discovery. And ultimately, we perform lateral movement to the machines that actually contain the sensitive data. We collect up that data, and we exfiltrate it out of the network. And the high-level finding that we had was that all of the AIs that we evaluated were capable of detecting this baseline attack. And this is significant because it means that for typical assessment activity that would be conducted, the AIs would actually stop the assessors. And so it would have an actual impact on the assessment activities that we're performing. So having seen that the AIs are effective against this baseline attack, we were interested in understanding whether or not we could bypass detection. So the first thing we looked at was obfuscation. So the idea behind obfuscation is that you change something about the attack such that you still accomplish the goal, but you do it in a way that's different and hopefully avoids detection by the AI. So one of the things you can do is try to use different tools or techniques to accomplish the same goals while generating different or lesser amounts of traffic that hopefully the AI is less sensitive to. We can also do things like going low and slow, right? By rate limiting the rate of our attack, we can hope that the AI no longer thinks that this is suspicious activity. We also looked at things like trying to perform our attack steps using machines of users that already perform similar activities as part of their job duties. So if we need to muck about with some databases, we try to do that from the database administrator's machine because that's a lot less suspicious than if we did the same mucking about from the intern in accounting. Based on these obfuscations, we then defined and executed a modified attack path, and we wanted to see if the AI could still detect it. Now, the modified attack path was actually fairly straightforward. We just reconfigured some of our tools. But that reconfiguration was critical. That was the difference between the AI detecting our attack and not detecting our attack. As soon as we reconfigured our tool, we were still able to accomplish the goal of the attack path while completely bypassing detection by our AI. The second thing we looked at was data poisoning. So the idea behind data poisoning is that you create this poison data, and you create it by performing benign activities that generate traffic that's similar to the types of traffic that you're going to generate during the attack. This poison data then becomes part of the training data for the AI, and it causes it to mislearn, right? You want the AI to think that the attack traffic that it's going to see is just normal background traffic. Of course, we took care to ramp up our poisoning slowly. It does us no good if our poisoning itself is what gets caught by the AI. And our finding was that the data poisoning enabled the attack path to completely bypass the AI defense. It mislearned, in fact, and no longer was able to catch the attack that we were launching. So to summarize the findings that we had, we found that the AIs we examined were capable of detecting our baseline attack path, and thus would pose an impediment to some of the assessment activities that we would normally do. However, by doing data poisoning and by doing obfuscation, we were able to then evade detection and still get past the AIs and into the network. So that's what we've done. Where are we hoping to go in the future with AIDE? So there's quite a few directions we're hoping to go. First, we're always looking to increase the realism of our traffic and our system environment. So for example, we're hoping to get some video conferencing software like Zoom or Skype installed so that we can simulate that kind of traffic on the network. We're also hoping to use replay traffic because while we took a lot of care to define out this organization and to generate the traffic based on that organization and the users in that organization, there's no substitute for using actual traffic. And there are some technical challenges associated with convincing the AI that replay traffic is actually live traffic and of injecting an actual attack into replay traffic, but those are obstacles that we think we can overcome. We're always looking to expand out the range of attacks we consider in our methodology. We looked at a single attack path in this current work, but we're hoping to get that up to hopefully dozens. We're also always looking to increase the number of AIs that we're actually evaluating to get a better sense of the landscape of these AIs. In this project, we looked at an evaluation at a single point in time. We had that snapshot that we evaluated against. But you'd like to be able to know that, to have some assurance that your AI is going to work a couple weeks down the road, or a couple months down the road, or a couple years down the road. And that requires an evaluation over the course of time. And we're looking also to try to extend some of the testing and evaluation methodology that we've developed here to other types of AI systems, not just AI network defenses, but maybe other types of systems in cybersecurity, like endpoint detection software, or perhaps outside of cybersecurity altogether. And I'll throw it out there that we are actively seeking collaboration opportunities. So if anything that you've heard here today seems of interest to you, or you're interested in applying some of these techniques to other types of AI systems, please reach out and let's see where we can engage. And finally, let me close by just thanking the team that worked on this project. This is not my work alone. We could not have accomplished this project without the help of Dr. Grant Deffenbaugh, Cheslea Cribbs, and Brandon Marzik, and our interns Reggie Savoy and Alec Woods. And with that, I'd like to thank you very much for your time and attention, and I hope you enjoyed the other presentations.